Okay, and now I'm going to use the expressions that I know about for these energies, which are of course 1/2 mv squared, and that's mv I squared, plus 1/2 a moment of inertia omega I squared, and that equals, let me see if I can save myself just a little bit of time. Pasting it in over here and fixing a couple of things. So I have final kinetic energy. May have saved me just a few seconds, but especially has saved me trying to write with this pen. Plus, then the potential energy is mass times gravity times height. So here's our equation, quite a bunch here and quite complicated looking. And let's see what we got. Well, we're supposed to figure out what's the final velocity when the ball is up here, which means we're looking for this VF. We have given this VI, the initial velocity. So the initial velocity is given. I'm going to make a check mark there. Again, it was supposed to be an I. And then VF. Make this look just a little nicer here. Hopefully VI. That always smears. And this is what we're supposed to figure out. And now it gets interesting because there's also the final angular velocity, and there's the initial angular velocity. And do we know that? And so we actually have three variables, and we'll see in just a moment what's going to happen. And then there's the mass in here, which is not given in the problem, but I think we can kind of assume, as we're familiar with the energy equations, that the mass will divide out at some point. And then there's the moment of inertia in there, which I also substitute in just a moment. And then of course there's the height there. I might as well write that one down. The height, that one is given 0.76 meters, and gravity of course is implied. Let's see. Okay, I'm going to change the colors here, because what I'm going to do now is I have like these three unknowns here, omega f, vf, omega I, but these two here are connected to the velocities, and we look in the previous chapter that the angular velocity equals the translational velocity divided by the radius, which introduces another variable actually, because they don't give us the radius. What's going to happen there? Well, you'll see in a moment. I'm going to write down the moment of inertia for the solid sphere. So that's going to be 2/5 mass times radius squared. And I know they're writing capital R. I'm going to write capital lowercase r here. And I think you can see that already. Once I substitute this expression in here and this one here, and of course over here as well, then I'm going to end up with an r squared here, and I'm going to end up with divide by an r squared here, and the radius is gone again. I introduce it, but it's gone right away, and that's why they don't give us the radius. Also, once I substitute the moment of inertia here and there, then each singular term takes on m, the mass, and therefore it cancels out or divides out, and kind of like I suspected earlier, the mass, we don't need it. So no matter what the mass is of the bowling ball or what the radius is of the bowling ball, the outcome is the same and just depends on the rise and the shape of the ball. That means if it's a ball, if it's a cylinder, if it's hollow, if it's solid, and that's where this factor here, 2/5, comes in. Okay, now I'm going to substitute that in there, and that's going to be a lot. I actually thought that I'd already cancel the masses as well as the r's in there, but then I reconsider and figured, well, I might as well write it down, even though it's going to be really long here. So I'm just going to write everything down and then divide everything out. And let's see, r squared, and then times, and this is the omega squared, so it's going to be vi squared divided by ri squared. And now I'm going to copy this entire expression and write it over here and virtually run out of space. I'm going to get rid of those. Ooh, that's going to be interesting. I'm going to try to get rid of those i's and write down f and f. Oh, I don't need an I for the r. The radius is the same either way. Whoops. And then I have an equal in between there. And so here's the initial rotational and kinetic energy, final kinetic and rotational energy, and then of course plus the potential energy. Okay, at this point already, if you look carefully, you will see that there is only one variable, Vf, right there, and everything else will either divide out or is given. So here's the r that divides out. So here's the r squared that divides with this here, and there's the r squared that divides with this here, and then each single term has the mass given in it, and that's why we don't need it, and it divides out, and then the entire expression looks somewhat nicer. Here's what I'm going to write: 1/2 times vi squared, and over here it's 1/2 times 2/5 times vi squared, and that means that both of them have a 1/2, and then this one here has a 2/5, and of course this one here has 5/5. So keep that in mind: 5/5 over here plus 2/5 over there, and that of course is 7/5. You know, when you add 1 to 2/5, then you come out with 7/5, and you would have to understand this for this class. You know, I'm doing physics here, and you would have to understand the math, definitely. In fact, I was even considering, just writing this down with all the r's and without all the r's and m's, and let you do that, because you're supposed to understand that. And then on the other side, I have 1/2, and again, it's going to be 1 here, which is 5/5 plus the 2/5 over here, 7/5 Vf squared, and then plus GH. Of course, the 1/2 is not dividing out because it doesn't appear with the potential energy. And then it's a matter of plugging in the numbers here, subtracting this one here, dividing first by these two fractions, so dividing by 7/10 first, and then take the square root of the entire number, and you're going to come up with, because you take the square root, you're going to come up with a positive and a negative square root, but the ball rolls to the right, so you have to choose the positive velocity, and that's going to be in meters per second. If you look at the units, you will figure that out.